we've been working our way through second order ordinary differential equations. And in previous lectures, we've motivated the study, we've looked at the method of undetermined coefficients and how to solve problems with constant coefficients in the equation. Today's lecture is the next step, variation of parameters, sometimes called variation of constants. Now, some of you may have seen the first 3 topics up there last year. In fact, a lot of you would have if you're students here. What we're looking at today will be genuinely new to you. Okay, so the subject of this lecture is the method of variation of parameters, or sometimes known as variation of constants. Okay. So the differential equation that we're looking at here, the general differential equation, is equation 1. A, B and C are just known constants. G of x is some given function, like x squared or cosine x, e to the x, something like that. And the question is, given A, B and C, those numbers, and the function g of x, how do you find the unknown function y of x? Remember, when we solve differential equations, we're looking for a function as our answer. Okay? Now, the L here is just a linear operator, and the reason I'm using this L of y is because it simplifies the notation. You don't have to write down everything, just write down L of y to denote the left-hand side of the differential equation. Okay, so how do we solve equation 1? Well, we know that the solution has a special form, right? We talked about this before. Okay, it has this form y equals y sub h plus y sub p, where y sub h is a solution, or I guess the general solution, to the homogeneous problem. Okay? And this y sub p is a particular solution that we construct in some way to the original, more general, non-homogeneous or inhomogeneous problem. Okay, so in previous lectures, we've learnt how to build y sub h. Essentially, you look at this equation here, you write down the characteristic equation, which is a quadratic, you solve it, you look at the roots, and then you analyse the kind of roots that you have. And what you do is you form 2 linearly independent solutions, y1 and y2, and basically y sub h is just all linear combinations of these 2 solutions to the homogeneous problem. Okay, so the next question is, how to construct a particular solution to homogeneous equation 1. And we have discussed that in previous lectures, but only for a limited number or a limited style of right-hand sides. When g of x is, say, a polynomial or an exponential or a cosine or sine, then we can make a guess with our y sub p based on the form of g of x. That doesn't always work, though. Okay, so for example, if g of x was tan of x, you couldn't just make a guess for your y sub p when we looked at the method of undetermined coefficients. Okay, so this lecture gives you another way of constructing a particular solution to the non-homogeneous problem. Okay, and the method is known as variation of parameters or variation of constants. Okay, so to construct y sub p, a particular solution to the non-homogeneous problem, what we do is assume that y sub p has the following form. Now, notice what we're essentially doing here. See, y1 and y2 are just from here and here, from the homogeneous, the solution to the homogeneous problem. Okay, so essentially what this does is it assumes that you can build y sub p from y sub h, the homogeneous solution. Okay, now the v1 and the v2 are just some functions that we want to determine. Okay, so v1 and v2 are some functions that we want to determine. If we know v1 and v2, then we can write down y sub p. Okay, so we're building y sub p from y sub h in some way, based on these two functions. Okay, now, how do we do it? Well, if 4 and 5 are satisfied, then this form, y sub p, will solve the non-homogeneous problem, 1. Okay, well, to see this, all we really want to do is show that this, L of this equals g of x. Okay? L of that form of y sub p equals g of x. Now, if you do that, so you essentially apply L to this form, so you basically are differentiating this once, twice, and then using your linear operator L. If you do that with a little bit of algebra, and of course the product rule, because you've got products of functions here, you can come up with the following representation. And again, I've just used L of y1 and L of y2 to save a bit of space here. Now what we want to show is this can be reduced down just to g of x somehow. Okay, well, let's go. It looks quite complicated, but let's go into it and see if we can simplify it. Well, firstly, y1's a solution to the homogeneous problem, so this is just 0, L of y1 0. Similarly, L of y2 is also a solution to the homogeneous problem, so L of y2 0. Now, by assumption 5, this part here is just g of x over a. By assumption 4, this bracket here is just 0. So you can see actually there's a lot of cancellation, a lot of things are just disappearing there. So it's not that difficult. Okay, so all you've got to do now is simplify this and this. Well, you can see the a's are going to cancel. Well, from 4, if I differentiate both sides of 4 and use the product rule, I'll get this. So what does that mean? Well, if I just sort of forget about that and rearrange some of this right-hand side, I'll get the following. Okay, so what I can do is replace this with this and get the following. Okay, so basically I'm going to substitute out and simplify, and I'll be left with a g of x when I simplify. Okay, so what does it mean? Well, it means that this will be a solution to the homogeneous problem. The non-homogeneous problem, the general problem. Okay, so that's why it works, but the question is, the real question here is, how do you find the functions y1 and y2? Well, I'm glad you asked. You can get them from these two equations here. Okay? Equation 4 and 5 are just some simultaneous equations in y1 prime and y2 prime. We know what y1 and y2 are, so we know what y1 prime and y2 prime are. We know what g is, we know what a is. So what I can do is solve 4 and 5, find y1 prime, y2 prime, and then integrate them. That's all it is. Okay? So think of these as simultaneous equations, in a sense. Okay? Once we have y1 and y1 prime and y2 prime, we can integrate them and throw them in here and get our particular solution. Now, we can solve 4 and 5 for v1 prime and v2 prime, provided the Wronskian is non-zero. Okay, so in matrix form, you can write out 4 and 5 in this form. Okay? And what you can do then is solve it somehow. Here I've calculated the inverse of this matrix. And you know that this solution will have this problem will have a solution if and only if this Wronskian, this determinant, is non-zero, right? So what I can do is calculate v1 prime from just expanding this, v2 prime from this, and then integrate. So here are explicit representations for my coefficient functions v1 and v2. Okay. Now this is important. I'll show you how to do some problems involving this method in a minute, but you don't need to remember this, at least for this course. Okay, the formulae will be given to you. Okay, it's good to know where it comes from, of course. You know, because a good question is, well, why should the Wronskian be non-zero? Well, if you want to solve for these things, the determinant's got to be non-zero, right? Okay. So here it is in a nutshell, the method of variation of parameters or the variation of constants. Suppose you want to solve this non-homogeneous problem. You solve these equations for v1 prime and v2 prime, and then you integrate. Okay, so you find these coefficient functions, v1 and v2, and then to solve the whole thing, it would just be the solution to the homogeneous part plus the solution to the particular solution to the homogeneous, non-homogeneous problem. But that's a lot to remember. I don't expect you to derive these things in an exam, right? You'll be given a formula for this. All you really need to do is calculate v1 and v2 from that formula. So let me show you how it works in practice. All right, here's a question. Now, you can't do this using the methods from the previous lectures. So how do we apply the variation of parameters or variation of constants to this? Well, first of all, solve the homogeneous problem, right? So we're given some information there, but what you would do is you would make that right-hand side 0 to form this homogeneous problem. You would write down the characteristic equation, which is that. You would solve it. You're going to get real and repeated roots, r equals +1 and r equals +1. They're repeated, so the solution to this problem is of this form, where big A and big B are constants. Okay, so how do we put the y sub p together? Well, let's think of this. We use the solution to the homogeneous problem. Think of this as the following. So in this case, the function y1 is e to the x, and the function y2 is x times e to the x. Now let's have a look at the Wronskian for these two functions. Okay, I mean we already know that they're linearly independent, right? But we need to calculate the Wronskian if we're going to use it in our variation of parameters formula. Okay. So if y1 is e to the x and y2 is x e to the x, we need to calculate their derivatives. Okay, so that one's easy. And this one I'm just going to use the product rule. So what I want to do is look at the determinant of this. I'm going to get that times that minus that times that. Now if you do a little bit of algebra there, you'll get e to the 2x, which of course is never 0. Okay? So that kind of, having the non-zeroness there just sort of confirms that these things are linearly independent. So we can work with them. Okay, so now let's build a particular solution to this problem. Okay, so our right-hand side, say g of x is e to the x over x squared plus 1. Okay. So what we want to do is build these coefficient functions, v1 of x and v2 of x, and then I'll have my particular solution. Once I have my particular solution, I just add it to my homogeneous type solution, and then I've got my general solution. Okay, now going back to this representation here, we're going to use both of those to calculate v1 and v2. Okay. So let's just calculate those separately. Now just to save a bit of space, I'm not writing in the x's. Okay, so y sub 2 is x e to the x. G is e to the x over x squared plus 1. And W is e to the 2x. Now that looks a little bit messy, but I can cancel off the exponentials in that setup. Okay, so if I cancel the exponentials, I should get something like this. Okay, so this integral now is going to be something like a logarithm. So I'm going to get something like this. X squared plus 1 is always positive, so I don't need to put absolutes here. I just need to touch it up a bit, something like that. Now I don't need to worry about the constant of integration. Okay, so that's v1. So I've got half of my y sub p. Let's move on to v2 now. So again, we would just use this setup here. Okay. The a is 1 in this case, by the way. Okay, the coefficient there. All right. All right. So for v2. So that is just the following. Okay. So, I guess I should put it in there just for this case. But A is just 1 in this case, so it doesn't really matter. Okay, so y1 is e to the x. G is this. So let's sub that in. W is this, A is 1. Now again, you can see some cancellation going on here. The exponentials are going to cancel out, and we're going to be left with something like this. Okay, so we're going to get something like an inverse tan for this one. Okay, well, what we can do now is we've got v1 and v2, these coefficient functions. Let's combine them and write down y sub p. So y sub p is v1 times y1. So my y1's e to the x, so I'm going to get something like this when I combine. And my v2 y2 is going to be something like this times x e to the x. Okay, well, last step, let's combine y sub h and y sub p. So let's call this star, let's say. Okay, so this is going to get a bit messy now, but we have the following. We got there. Now, can you see how the homogeneous solution in this case has nothing to do with this form? Okay? Very powerful. Obviously, you've got to be on top of your integration for these kinds of problems. But rest assured, if we ask you something about this, even in class test 2, we'll give you the variation of parameters formula. Okay, so you don't need to remember it, you just need to be able to apply it. Okay, so the big A and big B here are just arbitrary constants. We don't know what they are. We could calculate them if we had initial conditions, but we don't. Okay, questions? So those, as you can see, the solution's quite involved. You'll get faster as time goes on, of course, but the solution, you have to calculate a few different things, v1, v2. Okay. Here we're given another second order ODE. Now, in this example, we're given the solution, general solution to the homogeneous problem, and we're asked to calculate a particular solution, y sub p. Okay, and in this case, they want you to use the variation of parameters method. So the underlying idea here is to take the homogeneous solution and build a particular solution, okay, from the parts of the homogeneous solution. Okay, now, essentially it's just applying the formula. So you can think of this function, cos x, as y sub 1, and this function, sin x, as y sub 2. Okay, now they are linearly independent, but we're going to have to calculate the Wronskian anyway for our formula. All right, so you can think of g of x as your tan x. All right, so the Wronskian is just the following. It's the determinant of this matrix. So let's write in our y1 and y2. Form the derivative of y1. That's going to be something like minus sine x. And if I differentiate sine x, I'll get cosine. So the determinant here, it's going to be cosine squared plus sine squared. Yeah, so we're going to get 1 there, which is non-zero. Okay? So now let's build the particular solution from these y1 and y2 functions. Okay, what we're trying to do is get these coefficient functions, v1 and v2. If we can calculate them, then we've got y sub p. Okay, let's calculate, say, v1 first. Again, I'm going to go back to this formula here. Now, the a, in this case, is, again, going to be 1, the coefficient of y double prime. So a is just going to be 1 in this case. Again, I've left off the x's just to save a bit of space. Okay, so y sub 2 sine x, g is tan x. So what I can do is write g as, say, sine of x on cosine x. It's actually going to simplify it a little bit. And a is 1, w is 1, so we get this. Okay, so we've got to integrate something like sine squared over cosine. Now, there's probably a few ways you could do this integral, but I'll just show you one way. I'm going to change the sine squared to a 1 minus cosine squared. And then break that up into 2 parts. So I'll get something like 1 on cosine, which is sec, minus cosine x. Okay, so the integral of sec, that's not easy. I suspect if you got a question like that, you'd be given the table, well, you probably have a table of integrals with you, at least in the end session. So the integral of sec, what's that going to be? Something like log sec x plus tan x, or something like this. If I integrate this negative cosine, I'm going to get something like sine x. Okay, so don't be too concerned about this integral of sec. I suspect if we asked you an integral of that nature, we would give you some hint or some table for it. Okay, so that's v1. Yep. So let's get on to v2. Again, we'll just calculate v2 from this setup here. v2 is a bit simpler. Okay, so in our case, y1 is cosine x G's tan x. So A is 1 and W is 1. Oh, sorry, that should be a cosine. So again, I'm going to write tan as sine x on cosine x, because it's going to simplify. A times W is 1 in this case. So I can cancel off the cosines. I'm integrating sine. I'll get minus cosine x. Okay, so all I need to do now to calculate y sub p, take my v1, multiply it by y1. Take my v2, multiply it by y2. Okay, so v1 is going to be something like, the first term is going to be something like this. And the second term is this times this. Now, if you look closely, two terms are going to cancel out. You've got a sine x cosine x and a minus sine x cosine x. So actually the answer here is just going to be the following. So I'm going to get something like minus cosine x log sec x plus tan x. So that is the a particular solution to the homogeneous problem. Questions? Fairly involved question, right? There's a few things to do there. It's not just solving a quadratic equation. You can if you want. That's a very good question. I think the question that Alex is asking here is, why if we know this method, why have we learnt this method of undetermined coefficients in the previous lecture? You know, where you make a guess, or you know, if g of x is 2x plus 3, let's make a guess, cx plus d or something, calculate the constants. Well, you can see this method's quite involved. It's not always necessary. Okay, why would you go through all that pain when the right-hand side's an easy function? If the right-hand side's an exponential or 2x or something, polynomial, why would you use this method? Okay, but if it's a bit exotic, like tan x, ooh la la, you've got no choice. You have to use this method. Okay, because the method of undetermined coefficients won't cut it with this right-hand side. Okay, but it's up to you. It's up to you. Any other? There were some more questions. Who was asking questions before? Someone. Oh, right. Oh, good. So, yeah, you have the freedom to use this method wherever you want, but it's not always the most efficient. It's not always the most efficient. Now, so I wanted to do this one. This one's as hard as it gets, I would think. It is similar to the previous one, but the thing that is a little bit nasty is this 3x rather than just x here. Okay, so let me show you this, but this is right at the top of the scale. We're not given the solution to the homogeneous problem in this case either, so we have to compute that as well. Now, I think you've got 3t here. I've just made 3x just to keep everything consistent. Okay, so let's compute the homogeneous problem associated with this. Okay? Once we've found that, we can then build a particular solution out of it using the method of variation of parameters. Okay, so the characteristic equation, we won't spend much time on this one. The characteristic equation for this, it's going to be something like r squared plus 9 equals 0. So we can solve that. It's going to have complex roots. R is going to be positive 3i and negative 3i. Okay. Now we know when we have complex roots, the general solution is a linear combination involving cosines, sines, and exponentials. Now the real part of this root is 0. So actually the solution for this one is just going to be something like this. Okay, big A and big B are just arbitrary constants. We don't know what they are, but we could calculate them if we had some initial conditions. Okay, so that's part one. Let's label this function as y sub 1 and label this function as y sub 2. We're going to now build a particular solution to the original equation based on y sub 1 and y sub 2. Okay. Let's compute the Wronskian of these two functions. So it's going to be something like y1, y2, y1 prime, y2 prime. So if I do a little bit of differentiation, I'm going to get something like minus 3 sine 3x and 3 cosine x, 3 cosine 3x. Now if I expand this, I'm going to get something like something involving cosine squared plus sine squared. Okay? The 3's out the front give me an answer of 3. Okay, again, it's non-zero. Okay, well, let's use the following form for y sub p. And once we calculate v sub 1 and v sub 2, those two functions, we've got our y sub p. Okay, so we just need to do a little bit of integration to get this coefficient function and this coefficient function. Okay, so here again, A, the coefficient of y double prime is just 1. G is 2 tan 3x. y2 is sine 3x. So I'm going to get something similar to what I had in the previous one. And I'm going to write tan as sine on cosine. So I can bring that 2 on 3 out the front. And I have a sine squared there, sine squared 3x. So what I'm going to do is change that to a 1 minus cosine squared 3x, and then break it up similar to the previous problem. Okay, I won't put all the steps in, but I'm running out of space. So to integrate sec, it's going to be something like log sec plus tan. So if I do these integrals, I should get something like this. Okay, so that's v sub 1. That's the most complicated part. The integration involving v sub 2 is not too bad. So y sub 1 is cosine 3x. G is 2 tan 3x. So I'm going to write that as sine on cosine. And I'm dividing by 3 here. So I can cancel off the cosines, and then all I'm doing is integrating sine 3x. So when I integrate that, I'm going to get something like minus cosine. Okay, so I've got my two coefficient functions. What I want to do now is put everything together. Y sub p is in this form here. So let's just take what I've just calculated, multiply through, and I should get the following. Okay, and the other part is going to be what, v sub 2 times y sub 2, so y sub 2 sine 3x. So again, if you look closely, you're going to get two terms cancelling out. So let me move that up a bit. There we go.